Hi, my name is Perry. I'm a production engineer working on release engineering at Instagram, the world's largest Python site. Let me tell you a little bit about myself before I begin. I've been at Facebook for the past 4.5 years. I worked on our internal CI system called Sandcastle for 2.5 years initially, and for the past 2 years I've been working on Instagram release engineering. I'm also a badminton enthusiast, which it turns out is extremely popular in Singapore, so I'm glad to find that. This photo is a picture of my teammates and I in our very Instagrammable headquarters in Menlo Park. Now that you know a little bit about me, let's talk about the state of server release. At Instagram, we operate a very large fleet of web servers serving Instagram.com. Every weekday, we deploy the site around 70 to 100 times during the working hours. I cannot emphasize enough how large and insanely fast this deployment is. I've worked at smaller companies with smaller pushes that deploy maybe once, maybe twice a week, with less than a very small percentage of the machines that we operate with at this scale. So it's kind of amazing to see this in progress every single day. So in this talk, I'm going to walk you through the history of our deployment system, sharing some of the insight from along the way, from our evolution from a small deployment script to a lightning-fast, complex automated rollout. What I want to give you in this talk is that everyone can identify with some stage of our deployment history. I hope you can use this as inspiration, or just use it as a blueprint and straight up steal our deployment system and take it back to wherever you are. So with that said, let's go back in time to our humble beginnings. Just like everyone else here, we started off with a simple deploy script. You can easily use an open source Python tool called Fabric to go and automate this process yourself. Whatever the process is not extremely important. There's a set of manual steps which you use to deploy code to new machines. Anyone can understand this system and deploy the site themselves. So let's see how this evolves over time. In order to truly allow anyone to run this, we need to ensure that there's locking to make sure that there's a consistent deployment across the site. You don't want Bob and Alice deploying their code simultaneously to different machines all across the fleet. Additionally, Instagram has had a strong culture around testing for a long time, so it was easy to run our test suite before deploying to ensure some basic level of sanity on the fleet. However, tests don't catch everything, so we built a simple canary process that compares metrics like HTTP response codes across two small sets of a deployment. As you can see here, we have two deployments that we're comparing the dinosaur view on. And you can see that in the canary and control, the HTTP 200 status codes are relatively the same, so we can reasonably say that this is not going to destroy the site. As more and more people deploy the site, though, it becomes harder to track which commits are being deployed by who and when. So we built a simple system to basically just track the commits and when they were getting deployed. With this data in hand, it was easy to notify the diff author that their code was being deployed. This is good because the commit author generally knows when to be around to support their changes, and the commit author is generally the person who knows what their code should and should not be doing in production. When we increased the number of servers we had, it was another simple incremental change to parallelize the actual push stage. You can see this was a simple time. We had a single deploy script to deploy our entire website that grew over time and was responsible for deploying the website for many years. Because our script was shared and changes were small and incremental, it allowed us to develop a process which remained largely intact since then. So what didn't work well? People. We wanted to empower engineers to deploy their own code. However, just because you can deploy doesn't mean you will deploy. Let's say I land some code on a Friday night and I promise that I will deploy it by Monday morning. Well, now let's say Lisa has to go and fix the site over the weekend. It's a Saturday. She needs to push a hotfix. They deploy the code, and all of a sudden, some unrelated product starts breaking. It's very confusing and time-consuming to figure out that an undeployed change was actually the cause for the new production breakage. So how do we address these inconsistencies? Just don't trust humans. The deployment script relied on human consistency too much. Most questions have a pretty sensible answer. Do you want to run tests before pushing? Yes. Test failed. Do you want to continue? No. In fact, the sensible answers work quite well in most cases. Only in exceptional cases should we rely on a human to figure it out. So what do you get when you run a deploy script and a post-commit hook? Continuous deployment. This was the start of our continuous deployment automation. Many of you have all the ingredients you need to start your own continuous deployment today. Post-commit hook, deploy script. Continuous deployment gives us several benefits. The time between commit, deploy, and error is shortened immensely, which means it's much easier to figure out what change actually broke the site. Additionally, the smaller changes are just easier to reason about, and it's easier to debug the changes from one change as opposed to 20 changes. This represented a major shift. Instead of an action performed by every person, deployment became a service that was owned and operated by the deployment team. Engineers relied on the service to deploy their code after pushing it. Gone were the days where somebody would write a change and then just go and push it afterwards. Now people just let the deployment system take over. This is great. However, there were some unintended side effects. Fewer people knew how to deploy the site and roll the site back operationally. Additionally, as we hired more people, breakages became more common. Breakages that block deployment for everyone, which actually reverses a lot of the benefits of continuous deployment. And the deployment team became the bottleneck for the broken trunk, which is not scalable. It's unreasonable to assume that your single deployment team can be responsible for the entire company's changes. So how do we remove the deployment team as the bottleneck? It's pretty easy. Just don't break trunk. Breaking trunk blocks everyone. Post-commit fails and we can't deploy. So how do we stop people from breaking trunk? Well, let's talk about landing. At Facebook, we work off master. We do not use branches outside of a few special processes. This requires diffs to be rebased before pushing to master. We call the process of taking a change and applying it to master and pushing it landing. In order to stop people from breaking trunk, we built a land blocking workflow. First, we rebase, then we run tests, then we canary. Does this look familiar to anybody? We can also parallelize this process. Many things can land at the same time. This means that no longer is master a single bottleneck for changes getting deployed. However, once we land something, the order of commits matters. Let's say you have changes B and C, and independently they pass on a certain master revision A. Well, when they land, it may happen that B lands before C or C lands before B, and it could be that in some combination, some ordering, they actually just fail every request. So we still need to continue running our post-commit afterwards. But you can see that the post-commit is also parallelized. So as soon as we see that a revision is good, we can opportunistically deploy there and just continue the process. So what did this give us? The commit author is now responsible for making their changes work on master before getting into master. So they're unblocked. This means trunk is broken much less often, which means everybody else is unblocked too. This means that release engineering is no longer the bottleneck for getting changes out and for people developing their code. This is good for everyone. Additionally, fewer breakages mean commits are deployed more reliably, and we can establish a contract with our engineers. That means that we can reliably deploy changes within an hour of landing, and that hot fixes are fast. The major takeaway from this means engineers can be expected to be around when their changes are being deployed. Previously, if you pushed a change and somebody broke master, it could be hours before your change got out. If this happens frequently enough, you don't expect your changes to go out within an hour. If, however, changes going into master are assumed to be good, and you land a change, you can reasonably assume that your change is going to be pushed within an hour, and so maybe you shouldn't go to dinner or go to a movie in the next hour until your code pushes. But what happens when we miss something? We take the locks, controlling land to deploy and firefight. These are simple control mechanisms. They just stop the system from moving forward. Instagram has a good incident review culture. We always ask why it wasn't caught by tests or canary. This process and the culture tunes the deployment system, making it better over time, which means that the system is able to catch more and more subtle errors. However, tests and canary can't catch everything. Test coverage is good, but people make mistakes. Tests aren't perfect. Nobody covers all the branches in their tests. It's somewhat infeasible to in most cases. Canary catches things tests don't catch, but we need a lot of volume to catch errors. If 1 out of 1,000 requests, it turns out, is very bad or is failing, but it's a really important request, like a media deletion, that can be very bad. But canary will not catch it. So certain errors only become obvious at scale. So it takes us to our next phase in our evolution, deployment phases. Previously, canary was the final stage between master and deploying the site. Now we wanted to add an intermediate step comprised of about 2% of our hosts where we can sit and catch low firing errors. So for a single commit now, we're waiting a minimum of 24 minutes. And I can hear you thinking from the title, hey, how is this deploying every 7 minutes? It's true that the first deploy of the day will take 24 minutes. Because the process is pipelined, though, each subsequent commit can be deployed as quickly as they've passed the previous stage. However, at this point, the deployment system is getting way too complex. This deploy script is doing too many things and has become untestable. So finally, we threw away our multi-thousand-line deployment script and built a coordinated system of rollout components. We didn't really change a whole lot in this stage. We were just taking the existing process and making it more modular and easy to reason about. So let's take a look at that system now. Our entry point is still the post-commit hook, except now we push the results into a database instead of running the push ourselves. Next, we implemented a simple controller whose sole responsibility is determining the health of the various phases, you can see C1 and C2, and advancing the phases once the previous phase passed. Once we've determined what the state of the world should be for the phases, we have runners that are responsible for enforcing the state on their various sets of hosts, C1 and C2. Finally, on each web host, we have a simple agent called Smith, Agent Smith, that is responsible for serializing deployment updates and actually deploying the code on the machine. This system allowed us to codify the enforcement of the state we were informally enforcing before. Additionally, it decomposed a complex system into simple components which are testable and easy to reason about. This picture is not simple, but each and every single component is a fairly small, like Python program that you can easily test and deploy separately. So finally, we had a complex deployment system, but it was taking longer to get to production. The line for C1 and C2 evaluation is becoming longer and longer, and how fast we can move C1 and C2 really depends on how fast we can reload code, and how fast we really need to deploy. Well, it turns out you need to deploy as fast as you can. Deploying as fast as you can makes it easier for engineers to be around to support their changes because the time from committing to deploying is short. It makes it easier to reason about when the commit is going to go out. Additionally, our engineers do not slow down because the system is slowing down. The volume of commits and engineering productivity generally goes up over time. Better productivity, but also deploying faster allows us to batch less and minimize changes in a deployment, regaining some of the benefits of continuous deployment. So let's talk about our two mechanisms for going fast, really fast. So here's an ideal scenario. We have one commit in queue, and we can easily just deploy all the commits. Here's another ideal scenario. We have two commits in queue. Again, we can easily deploy them one at a time. What if we say have 20 commits in the queue? Theoretically, we could deploy about 8 times in an hour. We need to batch 3 at once to go through all 20. So if we balance between batching as little as we can and deploying with 1 hour landing, we can get things out in a reasonable amount of time with a reasonable amount of safety. However, deploying continuously means deploying during peak traffic periods. Ideally, that red band over there, we want to widen that so that we take less time to deploy. That also means that we need to have extra capacity sitting around just deploying. This isn't ideal. But what if we barely had to sacrifice any capacity? This is where we get into some magic that really makes Python go fast for us. USENIX, at Instagram, we use USENIX as a web server to serve our Django app. USENIX has an article on their website called The Art of Graceful Reloading. I encourage you to go and read it if you're interested in this process, but I'll explain it briefly. USENIX basically has a master worker model, as you can see. Essentially what we do first is we ask that first master to fork itself and create a new master. Once we have the new master, we have a small script that sits and looks at the status of the workers and determines which workers are idle. When it sees an idle worker, it asks the worker to cease executing on the old master and spawn a new worker on the new master. This means that we actually have 2 sets of code running on the same process tree. Through each iteration, we slowly move all the workers over so that the new master has all the new workers with the new code. Eventually, once all the workers are moved over, we re-exec the old master, we kill the new master, and then all of the children get reparented to the old master, which is now running the new code. And so we've effectively done like a hot reload of our code without sacrificing any capacity that wouldn't otherwise be idle. This has a couple neat properties. Firstly, it means that when we deploy during peak traffic periods, because we only recoup idle workers, we're only recouping a small amount of traffic. So we actually use less capacity at peak time to roll out, but we still roll out as quickly as we can. This means that when we're idle, or mostly idle, we can move more workers at a time and roll out faster. So it means that we move as fast as we can all the time. And this kind of sums up our deployment to this day. At each and every step of the way, we had some guiding values, which I'll reinforce now. These are the things which helped us at each point, like sort of determine what the next easy step was. So our first North Star is do the simple thing first. We never really had a grand plan for what like CI would look like at Instagram. We just did enough to scale at each step. When a step was repetitive, we replaced humans with a computer. When people were breaking trunk, we just make them pass some tests before they get into trunk. When we found production errors not caught by Canary, we introduced another phase. We still run our controller, and a lot of the deployment system is a cron job to this day. Push as fast as you can. A simple and important concept is that the regular push makes changes small and distinct. This is easy to debug. It's great for developer productivity. We care about developer experience, but we also care about the increased production safety. We're definitely emboldened to make aggressive changes when we know that they'll be rolled out quickly and safely, and we can always roll back. Finally, this is probably the most important slide. If you didn't pay attention to anything today, you should pay attention to this. Continuous deployment doesn't work without knowing if your changes are going to break or not, or if you know that things are working. We would never be able to build such a system without the culture around code quality and testing that's held to a high standard by the engineers at Instagram. If you're interested in our values around testing, come by the booth and chat with us today or tomorrow. But I'd like to emphasize again that you cannot do continuous deployment without good signal on your deployment. And that's how we release the world's largest Python website every 7 minutes to this day. Thank you. I think we have some time for questions now. Does anyone have a question? Sure. Sorry, can you start off with your name and where you're from?
Okay, my name is Vishal. I'm from Mercury, Japan. So I would like to ask you a question about, like, you do parallel canary release for different features, right? So my question is, like, when so do you have like just like some dedicated servers for canary release, or you have you select like at the time of canary release, you select this server can be canary, and you do not overwrite the previous feature canary release on that server. Like, are you getting my question? So when you are doing parallel, canary needs some time, like you said, 7 minutes. So
sure.
Is it that feature is overwritten if when you are doing parallel, or you have like multiple canary servers?
Yeah, so the question is, do we parallelize the canary process, and does candidate selection ever overwrite the other canaries?
Yeah.
Oh yeah, it's a good question. So the way our canary works basically is we select out of our host of production machines, we just select a handful of hosts and we say, hey, now you are canary 151. And then when we have another commit that we want to test, we take another set of hosts and we say, hey, you're a canary like 127. And then they run independently for the duration of the canary. The canary phase is 5 minutes, but it's true that we do take a certain amount of production traffic and just run sort of anything on it. But the compromise is that if we allow sort of potentially dangerous code to be run on a couple like machines with live production traffic, that will stop us from completely destroying the site later down the line. So that's the compromise that we make with Canary.
Thank you.
Hi, I'm Roy. I work at Bloomberg. I have a question about, so you guys deploy every single commit when you push outwards. If you don't notice a bug until it hits all your machines, what's your rollback mechanism for that? Do you revert the single commit, or do you actually hotfix it on the spot?
Oh, that's a good question. Let me go back to this picture. Okay. Yeah, so like I said before, like our process is not perfect, and sometimes things get through. Ideally, over time, fewer and fewer things will get through, but I mean, occasionally it does happen. So let's imagine now that something gets out to all of the purple boxes on the bottom, and there's some on-call frantically slamming buttons trying to get people to undo whatever somebody just rolled out. Because this system is an enforcement of state, and the state is stored in the database, a rollback is as simple as just saying like, hey, we changed C2 from like 100 to 101, change it back to 100. And then all of our runners basically go and enforce that state on all of the machines. So that in combination with our USENIX zero downtime rollout make it so that our rollback can really take as much as, it takes maybe around 3 to 5 minutes to roll the entire site back.
Follow-up question on that. How
Sure.
long do you keep a state for?
How long do we keep?
A state for. So if you're rolling back to a previous state, if you don't realize that you have a bug in production until an hour later, do you still have that state, or do you keep every individual deployment as a state?
Every individual deployment state. So we track the promotions one at a time. So we keep information about the deployments as we go. Does that answer your question?
Yeah.
Okay, yeah. Otherwise, like our web tier is stateless, so it's not affected by the rollout in that way. Yeah. However, an interesting case you bring up, if you see an error that was introduced by a change an hour ago, we're actually pretty reluctant to roll back an entire hour because of the way that we develop. So generally, we try to fix forward in that case if a change is really old. We try to fix forward. Yeah.
Thank you.
Sorry, do you have time for?
Oh,
Please.
oh,
Okay.
or-
So my name is Bayu. I'm from Tokopedia. So one of my questions that you're pushing code every 7 minutes, right? And
Right.
you mentioned canaries with a different version. So how does the semantic versioning and then list of change logs manage on your side? Because somehow do you store it, or do you keep it rolling like version 1 point something and then have a major release manually, or do you don't do that process at all?
Oh, yeah, that's a good question. So we track, and it depends on like which phase it's in basically, but once things are in master, because the order is sort of determined, we kind of use like just a monotonically increasing ID to version those packages, because that order cannot change. So even if they're tested in a different order, like the one that has commit A in it is going to be version 1, and the one that has commits B and A in it is going to be version 2. And so that's how we do the versioning once it's in master.
So sorry, one follow-up question. Do you track any changes on changelog manifest, or do you guys just keep rolling and then only take notes on the commit message?
So we don't, so I think your question is, do we differentiate between the files change from deploy to deploy?
Yes.
Oh, yeah. So we sort of just treat each commit basically as an artifact, and so we test the whole artifact. We don't really do anything in our deployment system specifically when different artifacts change, with a couple exceptions. Yeah.
Thank you.
Hi, Perry.
Hi.
I'm John from Bloomberg Tokyo. So my question to you is, simply from all these slides, I don't see any beta staging. So are you telling me that in Instagram you guys just deployed to prod and tested there?
Yes.
Okay.
So to be more specific, so like the Canary process does use live traffic. And that's because our philosophy in deployment is that you can take a lot of time to build a sort of duplicate environment that almost acts like prod, but things will inevitably be different in production. This is largely, this is a philosophy I think that's shared by a lot of people at Facebook in general. And again, like I said before, if we can sacrifice like a handful of Canary machines and like have them blow up on some real traffic to stop that from happening a couple minutes later across many, like 2% of machines, which is still a lot, and then to stop that again from happening in many more, 98% of the machines, that's definitely a trade-off we make. Additionally, things making requests to the backend, they tend to retry. So like let's say you're hitting it with the mobile app or something, the mobile app will try a couple times, and so if it hits a Canary, it'll go back and try again and probably hit 90% of the rest of the hosts that are working correctly. Yeah. But yes, we effectively test with live traffic for that.
Thanks. Yeah, I definitely remember the meme about, yeah, like we test in prod. So Thanks.
Sure.
Hi, following the question from the gentleman from the Bloomberg Tokyo, right? Yet I'm from Rakuten Wiki, Singapore. So you say that you deploy directly to production without beta testing or staging. So my questions are right. So in your slide, I don't see any human intervention, right? Because for your commit, if even related to the security issues or any like maybe it's performance issue, right? And you deploy directly to production, you got issue, and I mean it takes at least like 7 minutes to roll back. I guess 7 minutes. And what do you think about that?
So you're asking, what if somebody skips tests?
Yeah, you say that we don't just human, right? But without human intervention, how you prevent the security issue if your commit has security issue? Because you don't test on staging, you don't have beta, you deploy directly to production.
Oh, so how do we catch security issues? So catching security issues is kind of like a larger, it's kind of a larger problem that's not really solved by a deployment system. So it's infeasible for a lot of changes to sort of proactively make sure they're not causing security problems, and there's a lot of different processes that are involved with finding security problems kind of like after the fact, like white hat programs. And so your deployment system is, well, you can do certain automated things to make sure you don't introduce security problems, like cross-site scripting and stuff like that. You can't catch all security problems in a deployment system.
I'm not sure if my understanding is correct, but you say that it can be prevented before it's going to deployment system, which means that you need to have some review before the commit is merged to the master, right?
Oh yeah, so
Yeah.
we have peer review before a commit is pushed into master. You have to have peer review.
Also, but without the testing and staging beta environment, how you ensure that your security will be like, I mean, yeah, I mean,
So
your,
I mean, yeah. So the concept of like, what if you hire a bad actor? Is that your question?
yeah, yeah.
Oh yeah. So I mean, that's largely a vulnerability in many companies. I mean, if you end up hiring a bad actor, most of the sort of strategy to handle that is just don't hire bad actors, which is not a great answer. I'll give you that, but I think it's really difficult to ensure that like internal people don't do terrible things to your systems.
Yeah,
Yeah,
thanks.
yeah. And we're just going to take one last question.
Hey, hi, Gaurav here from LinkedIn.
Hi.
So one of the problems that generally a lot of big companies see is how do you solve the deployment inconsistency problem? Like there might not be every time that all of the deployments are done by the automated systems. There might be some emergency cases where deployment has to be attempted by engineers either via CLI or via UI where they trigger it manually. So, and there might be cases where some of the systems are down, hosts are down, and they are having not consistent version. I'm talking about probably a microservice architecture where hundreds of services which are being built simultaneously and being deployed in the system. So how do you tackle that?
Right. So in this case, if you look at our runners here, the runners are, again, like an enforcement of state. So what they do is they actually sort of sit in a tight loop and just like talk to all the hosts, and they say like, hey, host X, run version 101. Hey, host X, run version 101. If the host is already running version 101, it will do nothing. If the host, let's say, has been down for like a month and comes back up, it comes back up and the runner just says like, hey, go download version 101. And so the system is sort of like eventually consistent in that way. If a bunch of hosts turn off, that's something that we need to intervene in a different way. But as for like deployment inconsistency, we sort of rely on the runners in this enforcement of state model to make everything eventually consistent.
Does this runner go back and refer somewhere like a system where it knows that this is a consistent version which needs to be keep on enforcing on all of these boxes?
Yes, so that we have a sort of central, we have like a simple database that acts as like the state basically for the entire system.
Okay.
Yeah.
Okay. Thanks.
Cool, thank you all.